Okay, well, thank you very much. Good morning, everybody. So as Adway indicated, I'm going to talk about, again, ocean modeling, and this is a continuation of yesterday's presentation. And this talk is going to be covering parameterizations the main parameterizations that we use in ocean modeling. And I just wanted to start again with this particular plot that I showed on Monday. And this is again showing in the vertical axis time scale and in the horizontal axis spatial scale and various processes and or phenomena are included in this particular plot. And if we essentially sort of approximately frame the temporal and spatial scales that are actually resolved or contained with various model resolutions. This one is the sort of nominal 3-degree horizontal resolution of the resolution version of the model. This is our workhorse climate model. When I say ours, it is a model version that's heavily used in CMIP comparisons or in contributions to IPCC reports. So it's primarily coming from order 1 degree or 100 kilometer roughly resolution simulations. So as you can see here with the sort of black framed area, many of the processes, in particular, the most energetic component in the ocean, mesoscale in particular, are not really properly represented. And you can see that only partial representation of surface tides and various other processes. And on Monday, I also included sort of nominal tenth of a degree horizontal resolution. And then I also included this green box area to represent kilometer scale modeling. But today, essentially, we'll be talking primarily how we are going to do these in sort of in 1 degree and perhaps in tenth of a degree simulations. But I wanted to also highlight that regardless of what your horizontal scale or horizontal resolution is, down here in the lower left corner, you can see that we have vertical turbulent mixing. So regardless of your horizontal resolution, unless your vertical resolution goes down to order centimeters or so, you are not going to be able to resolve these, and they need to be parameterized regardless of it doesn't matter how high your resolution is. We are not going to be able to come down to these scales for representing them properly, or explicitly representing them, I should say. So not just in ocean modeling, but in general, in modeling, Earth system modeling, parameterizations should accomplish physical effects of unresolved subgrid scale processes, and they are usually expressed in terms of resolved fields. They should be physically based, and you should be able to physically justify them. They should be as simple as possible, and ideally, they should be also as inexpensive as possible. And they should also have as few parameters as possible. Once you in my view, there are 4 phases of parameterizations. One is essentially you develop a parameterization based on physical principles and also using process models, let's say. Then you implement your parameterization. Then you verify your parameterization. If observations are available, ideally you should be able to verify it against observations for a particular sort of aspect of your parameterization, whatever the parameterization is doing. If not, then you may need to look at other sort of process models and maybe larger the simulations. And then at the end, you are going to assess impacts of those parameterizations. In other words, is that particular parameterization doing what you intended it to do? So these are sort of 4 steps of a parameterization evolution. There are many parameterizations in ocean models, and some of them are listed here. Mesoscale ADs, they actually are used for mostly tracers. We have the horizontal viscosity parameterization, that's for momentum equations. We have the vertical mixing, and that's valid for momentum and tracers, as I said. We have the overflows, and I'll talk about that a little bit more. River runoff and estuaries, submesoscale eddies. Again, that's for tracers. Solar absorption, Langmuir circulation associated with surface waves, and bottom boundary layers. So in the interest of time here, I would like to just focus on the top five. And one reason is that I was heavily involved in development of at least the top, well, four of the parameterizations, top four, the first four bullet items listed here. So starting with mesoscale parameterization, this is almost becoming my favorite plot here. I'm going to show it again here. This is again showing ocean currents. And I think I neglected yesterday or the other day to indicate what these were. These are sort of streamlines of ocean currents, and the colors are indicating ocean temperatures. So the warmer colors are indicating warmer temperatures, and colder colors are indicating colder temperatures. The point that I wanted to make here is that you can see again that there are so many small scale eddy features. Some of them, if the length scales are order 100 kilometers or so, we tend to call them mesoscale eddies. And for eddies with length scales less than or order 10 kilometers or so, we tend to call them submesoscale eddies. So you can see that many of these eddies are present pretty much everywhere in the ocean, maybe more so along the latitudes of the Southern Ocean, but also Kuroshio extension, North Atlantic current, and Southern Hemisphere gyre regions. So they are actually the most dominant component of the kinetic energy spectra in the ocean. So how do we essentially incorporate their impacts in coarse resolution models? So ocean observations have suggested or are suggesting that, as I said yesterday also, mixing in the oceans primarily occur along isopycnals rather than across isopycnals. So that we tend to call along isopycnal mixing adiabatic mixing, and we tend to call cross isopycnal mixing mostly diabatic mixing. So I'm showing here schematically density surfaces, which are given in red here, and then the black lines, these parallel to black lines, are showing the ocean depth. So if the observations are suggesting that mixing should occur along density surfaces, any mixing that you have along a horizontal surface will cause spurious dipycnal mixing, meaning that mixing across density surfaces, and we don't want to have that. So in early 1980s and sort of mid 1980s, this was recognized, and the tracer equation, the bottom equation here is for tracers. It can be T can be for temperature or salinity, and what we are dealing here is the right-hand side of this equation. So these are now recognized. This equation is now recognizing that the mixing primarily occurs along density surfaces, along this red line here. So therefore, these diffusion operators, del operators, are actually rotated tensor operators, and they are now along density surfaces. And this kappa was introduced, that's a diffusion coefficient, it was introduced as an along isopycnal diffusivity coefficient. However, this is not the only impact of mesoscale eddies. And this was recognized in 1990, and Jensen-McWilliams parameterization was introduced. It's usually referred to as GM90. So they proposed, Peter Gent and Jim McWilliams proposed that eddies advect also, in addition to their diffusive effect, they advect tracers. So they came up with a relatively simple form of parameterization, and they introduced eddy-induced velocities. It's denoted as U star, V star, and W star here for the zonal, meridional, and vertical components. And they are chosen as in this form. They're essentially representing isopycnal surfaces And this S is isopycnal slope, and AITD is a diffusion coefficient, but it's essentially a diffusion coefficient for isopycnal thickness diffusion. And in this form, it is preserving its divergence free, and it also ensures global sink of potential energy, which is essentially trying to mimic what mesoscale eddies do. In this case, the model equations become like this. So in addition to a result Eulerian velocity component, you end up with an eddy-induced velocity component in addition to the diffusion along isopycnal surfaces. So I was lucky enough, before I get to some results, this parameterization mimics effects of unresolved mesoscale eddies as a sum of, as I said, diffusive mixing of tracers along isopycnals. And there's an additional advection of tracers by a divergence-free eddy-induced velocity. The parameterization is valid for the adiabatic ocean interior. It's not valid in the upper ocean or near the boundaries where there's a diabatic. It is not adiabatic, it's diabatic. It acts to flatten isopycnals, and therefore it reduces potential energy. And with the advection term and with the diffusion term, it eliminates any need for pure horizontal diffusion. That was the case prior to this particular parameterization. I was actually just saying that I was rather lucky to start working at NCAR and at that time in early 1990s, and one of my first tasks at NCAR was to implement this parameterization in at that time our ocean model. It was based on an early version of modular ocean model MOM 1.4, and you can see that because of the computer power and all that stuff, all those limitations, what I called jokingly real ocean, 4-degree by 3-degree resolution in the horizontal, and we were able to run in this case, 20 vertical levels. So it's a rather coarse resolution model. And we were actually quite surprised by the impacts of this parameterization. It eliminated quite a few of the long-standing biases in ocean modeling. And I'm showing an example here. This is showing regions of where deep convection or deep water formation occurs in the ocean. And in the traditional approach, in which this parameterization was not used, everything was along density surfaces, there were a lot of regions in the Southern Ocean, in the North Atlantic and Arctic Ocean, where we were having a lot of deep water formation, which is not realistic. And we can see this is also the case. We can verify that thing from observations. When we implemented this parameterization, you can see that it is actually reducing potential energy, and it's making the water columns more stable, and we end up with deep convection or deep water formation occurring only in a few observationally known places, and that's the Weddell Sea, Ross Sea, and North Atlantic, Labrador Sea, and Erminger Sea and North Atlantic regions. Another impact of this parameterization, in interest of time, I'll just focus on the Atlantic sector here. This is showing the northward heat transport as a function of latitude. The observations are shown by this long dashed line here. For a long time, ocean models could not essentially get enough heat transport in the North Atlantic. They stayed rather low, and you can see that thing by the dotted line here. With this parameterization, you can see two examples of that thing, actually three, that we are actually increasing the northward heat transport in the ocean, in the North Atlantic, and that's associated with elimination of some spurious overturning circulations that were actually shortcutting the heat transport. Okay. One of the things that I should mention, just going back here, one of the main challenges in mesoscale eddy parameterizations is how to determine these diffusivity coefficients, in this case K and thickness diffusivity. And I'm aware of both in LEAP and M-squared lines, machine learning or AI approaches. This is one of the areas that they are focusing on, how to essentially use machine learning to parameterize these terms in the tracer equation. So this is a very active research area, even after 35 years of this particular parameterization. And the results are quite dependent on how you specify those parameterizations. Since our first implementation in mid-1990s, we of course worked on how to improve this parameterization by different definitions or different prescriptions for the diffusivity coefficients. And along the way, we also implemented a related parameterization. This is near surface eddy flux scheme. The idea here is that at the beginning, earlier, I indicated that GM parameterization, GM90 parameterization is valid for the adiabatic interior of the ocean. So we end up essentially artificially tapering the impacts of this parameterization near the, let's say, ocean surface. And that's not, I mean, it is what we do, but it's not necessarily the right thing to do. Simply at that time, we didn't know how to treat it better. And in sort of 2008 timeframe, in collaboration with a few other collaborators, we actually developed or implemented this particular near-surface eddy flux scheme. The idea behind it is essentially near the ocean surface, it is actually the mixing occurs across density surfaces. This is a schematic. The gray shading is indicating isopycnals. So in the ocean interior, we have these isopycnals. And the main mixing is occurring these with shown by thick blue lines along the isopycnals. And this is across isopycnal, dipycnal mixing. It's rather small. But as we approach the surface, isopycnals outcrop. And then the majority of the mixing occurs across these density surfaces. There is also substantial vertical mixing due to reduced stratification within the diabatic layer. Then in between, we called it a transition layer. So we ended up actually parameterizing this using an eddy-induced velocity profile schematically shown here. So we are using now, this is still what we use in POP today. And as opposed to a parameterization like this, shown by the dotted line, we end up using this parameterization. So this is what we think is more physical than our original implementation. Another thing that we incorporated is, as I was trying to say, is that how to describe or how to prescribe these diffusivity coefficients is still a big task. And in, again, mid-2000s, observations were sort of indicating that mesoscale eddies are upper ocean intensified. So in order to mimic that, we introduced a profile for diffusivity coefficient, and it is given like this. It is essentially determined or represented by the vertical profile of the buoyancy frequency. And as you may know, buoyancy frequency, this is n squared, is large near the surface, and it diminishes as we go below the boundary layer or below the mixed layer depth. So we ended up essentially using this formulation. You need to specify a reference diffusivity coefficient. And for n reference buoyancy frequency, we ended up simply using the buoyancy frequency value at either the bottom of the mixed layer or bottom of the boundary layer. And this creates a three-dimensional time evolving structure, which is actually perhaps, I mean, I would think more realistic than using a constant diffusivity coefficient. And this is a result that we published in late 2000s. This is showing the spatially varying eddy diffusivities. This comes from a combination of the near surface eddy flux and this n squared dependency that I just introduced. This is showing the upper ocean. I can't remember. This is like upper 100-meter mean or something like that. Year one and later structure for the diffusivity coefficient. And you can see that there's quite a bit of spatial structure in, for example, where the mesoscale eddies are important or strong, then we have larger diffusivity coefficients along the Southern Ocean latitudes. And this one is showing, the bottom panel is showing a zonal mean distribution. This should be the global zonal mean of the thickness diffusivity. And you can see the upper intensification of the diffusivity coefficients as that's how we constructed in a sense. And then these diffusivity coefficients are also enhanced in regions of subtropical gyres. So that is primarily used in tracer equations. So what do we do? What closure we use for horizontal viscosity parameterizations? And again, there are various options, but I just wanted to show you using a simple example what we do. So these two equations are, the top one is the zonal momentum and the bottom one is the meridional momentum equation. And just for simplicity, this is written in Cartesian coordinates. The diffusivities are isotropic, spatially uniform, and let's assume that for the purpose of illustration, our grid spacing is roughly 250 kilometers. There are four criteria that you need to be considering. One is grid Reynolds number. If you do not obey this, then you get diffusion noise, and this is the equation for that. So this is saying that your diffusion coefficient, viscosity, sorry, should be order 100,000 meters squared per second. This is a rather large number. Near the boundaries, you need to be careful and resolve, or at least try to resolve, boundary layers, western boundary layers. These are referred to as sort of the viscous monk layers. And this is the equation for that. And this is telling us that your diffusivity, viscosity coefficient should be 80,000 meters squared per second. If you want to obey numerical diffusive stability, that's the CFL condition, then based on the discretization that we have in the model, then that should be order 8 million meters squared per second. These are huge numbers. And for realistic representation of western boundary currents, for equatorial undercurrent, from the physics side, it's telling us that these diffusivity viscosity coefficients should be order 1000. So you can see that there is a huge sort of range that you need to satisfy. So what do? We ended up using anisotropic horizontal viscosity formulation, and I'm showing it here. By anisotropic, we mean here the diffusion coefficients are different as A and B. For example, in the zonal momentum equation, the meridional gradient or diffusivity of the zonal velocity is actually dictated by or influenced by a coefficient B as opposed to a coefficient A. We chose to do that because we need to have a B relatively small near the equator because we have really fast currents there. And if we have too large of a diffusivity or viscosity coefficient, then we end up essentially with really broad, unrealistic currents. And I'll show you an example of that in a second. If that coefficient is just too large, then we don't get anything essentially. This particular current system becomes too wide and too slow. So what we ended up doing is essentially we decided to go with minimally numerical viscosity or minimal numerical viscosity, and we want to have maximal physical viscosity, if it makes sense. So in other words, we are saying that we are going to live with some amount of noise. And in numerical modeling, and particularly ocean modeling, let's say, and to some degree in atmospheric modeling as well, viscosity is generally used to suppress numerical noise. So that's what we are essentially doing here. And so what we did is we are saying that we are not going to obey the diffusive grid Reynolds number, live with noise. We are going to resolve the monk layers only near the western boundary current regions. And elsewhere, for realism of the undercurrents and western boundary currents, we are going to essentially reduce the viscosity as much as possible within reason. And we need to monitor the noise structure, two grid point noise structures, to see whether we can essentially live with these small numbers. And we always, though, always obey the diffusive CFL number. Otherwise, the code blows up if we don't do that. So what is the end result? And as I was showing for the equatorial undercurrents, for those of you who are familiar with ocean modeling, this is showing a Pacific equatorial undercurrent structure. This is, I believe, at 140 degrees west. This is from observations. This is upper ocean, 300 meters, 10 south to 10 north. So you can see that we have a complicated undercurrent structure. If you do not use small viscosities near the equator, you end up with this kind of structure here. You can see that it's anemic undercurrent and rather broad. But if we essentially use what I just described on the previous slide, anisotropic viscosity with rather small diffusivity or viscosity values across the equator for zonal momentum equation, then we get a pretty good structure of equatorial undercurrent. So you can see that there's a really nice match in the current structure. Okay, what do we do with vertical mixing? As I said, regardless of your horizontal resolution, it doesn't matter whether you have 10-meter horizontal resolution. Even if your vertical resolution is still order meters or less, you still need to go down to less than or order centimeter length scales to be able to resolve. I'm using again resolve in a loose way here, vertical mixing processes. So that is not really realistic. So again, we end up parameterizing them. And in POP, and we are also using it in the new MOM6 model, we use the K-profile parameterization or KPP parameterization for vertical mixing. It was developed in mid-1990s, and then we later on in 2018 revisited some of its aspects. It was actually modified along the way, but then the final version, sort of revisited version, was actually done in late 2010s. So this is schematically showing sort of what we are dealing with here. This is the ocean surface. This thin line here is showing the ocean boundary layer depth. So we are interested in essentially uh, representing the vertical mixing that's happening within the surface boundary layer. This will be, of course, impacted by surface buoyancy fluxes. We have a variable free surface. There's penetrative shortwave going on here. And then within the ocean interior, and I'll show you those, we have additional components of vertical mixing. So then the idea is to somehow merge what's happening within the boundary layer with the ocean interior and to create a smooth diffusivity. So I'm not sure whether you are familiar with the turbulent closure schemes, but this is a first order turbulent closure scheme. In other words, we are expressing the turbulent unknown quantities in a sense. This is W prime X prime in terms of resolved or known variables within the model. So in this case, X is let's say temperature or salinity, or it can be zonal velocity or meridional velocity component. And we are interested in essentially parameterizing W prime X prime term. And what we do that, how we do it is simply using the down gradient approximation, and we introduce a vertical eddy diffusivity or viscosity. And in that case, this is parameterized in terms of the resolved temperature or salinity or velocity components. It's a first order scheme. And it involves, KPP involves three high-level steps: determination of the boundary layer depth, as I showed in the previous schematic. We need to calculate the interior diffusivities then as the second step. And then in the third step, we essentially match the boundary layer diffusivities with the interior so that interior diffusivities can be also used as a driver of the boundary layer diffusivities or boundary layer processes themselves. So how do we determine the boundary layer depth? And it is simply determined as based on a bulk Richardson number. Whenever this Richardson number given in this expression equals a critical Richardson number of zero 0.3, or it can be 0.25. That depth is determined as the boundary layer. Then in the interior, we have 5 components of diffusivity. One is shear instability contribution. The other one is internal wave breaking. This is usually referred to as the background vertical diffusivity. We have double diffusion. In certain instances, temperature and salinity, for example, can have different mixing rates. As I mentioned yesterday, also, if because of the hydrostatic approximation, since we don't have the vertical velocity tendency term, any kind of static instability or convection needs to be parameterized. So there's a diffusion coefficient coming from there. And then finally, tidal mixing. So interior diffusivity is actually diffusivity is represented as the sum of five terms. Then as a final step, then you essentially come up with the diffusivity profile, K profile parameterization, that's where the name is coming from. And it is determined as a turbulent velocity scale. H is the boundary layer depth we determined already. And then to match the interior and the boundary layer diffusivities, we use a cubic shape function. So this means that the interior mixing at the base of the boundary layer influences the turbulence throughout the boundary layer itself. So another machine learning sort of work that's going on again in LEAP and M-squared lines is how to determine this shape function. And there's actually now a method to replace that particular part of KPP with a machine learned approach. Tidal mixing. So as I said, the tidal mixing is added to the background diffusivity coefficient, and it is provided or given by the Osborne relationship. In this case, gamma is an efficiency factor of turbulence. It's usually taken as 0.2. Epsilon is representing energy, and n squared is the stratification. So energy is usually obtained in this form. There's the ocean density. There's another mixing efficiency or local dissipation efficiency. F is a vertical profile for the energy distribution, and E represents energy flux out of the barotropic tides, or energy available for dissipation. So I should mention that tidal mixing in this case is primarily mixing is enhanced over rough topography. So it is essentially this F function is large at depth where the ocean ridges are, and then it becomes smaller as you go higher up with an E-folding scale of roughly 500 meters. So how this parameterization is extremely sensitive to what energy field you use for dissipation, and also how you regularize your equation. I'll come back to that in a second, regularization. So this is showing 3 examples of available energy that you can input into the model. So you can see that depending upon how they essentially obtain these things, there are quite a bit of differences between these energy fields. So this will impact your results. But more important, well, before I get to this regularization, we also in the model consider tidal constituents, meaning that we treat semi-diurnal lunar and solar tides separately than the diurnal tides. And their mixing efficiencies can be different, and where they are applied in the ocean model. Through these, we can also implement or represent 18.6-year lunar nodal cycle in our model. I don't want to get into too much detail here because it gets quite complicated quickly. So regularization occurs in many places, and you can probably right away see that anytime you see a division like this, you should be really suspicious. What do you do if n squared is really small or goes to 0? So you can limit the value of n squared. It can be like 10 to minus 8 per second squared. or you can limit the resulting kappa diffusivity coefficient. And we tend to limit it, or I tend to limit it between 50 or 100 centimeters squared per second in our model. And I can tell you that what value you use for n squared and how you essentially limit this thing can impact your results quite significantly as well. So this is almost at that stage is an art form. We know we know the science, but the regularization becomes rather important. Overflow parameterization. This is, I worked a lot on this particular parameterization. And what are overflows? So I'm showing you, these are usually also called gravity current overflows. And this is a blow up of the North Atlantic. This is Greenland, Iceland, and Scotland is here. And in the North Atlantic, there are two major overflows. That's one of them is the Faroe Channel, and the other one is the Denmark Strait to the west of Iceland, between Greenland and Iceland. So there are actually dense water formations occurring in the Nordic seas, and they actually flow into the northern North Atlantic, and they form they contribute to the lower branch of the Atlantic overturning circulation or thermohaline circulation. And they are actually really, in addition to large, fine horizontal resolution, your vertical resolution needs to be order 1 meter or finer to actually represent some of the physics associated with these overflow waters. And that's really not feasible in today's Earth system models. So we ended up essentially in a z-coordinate model, in a level coordinate model. This is the bottom topography. This is Atlantic, this is Arctic. Surface is shown here. We have the Nordic Sea sides where the dense water sits. So in a regular z-coordinate model, in order for this upper dense water come down all the way to the Atlantic side, it has to go through an advection, convection, advection, convection, advection, convection cycle. And that in turn introduces really spurious entrainment, and the water gets diluted. Instead of going all the way to the bottom, it ends up staying in the intermediate depths, and that's not what we want. That's a major issue with level coordinate models. So what we implemented here, we actually implemented so-called stream tube model, and what we do is we actually pipe the flow through the rock or through the rocks. We essentially pipe the flow into the rock, take it down, we get the entrainment through the rock, and then just we insert the whatever the product water is into its appropriate depth. And this is again a rather complicated parameterization, and I'm showing another schematic here. So we have the mass or volume flux coming in into the topography area, shown by the red line here, or red arrow. Then it goes pipes, it gets piped down, but in between we use single point entrainment parameterization to essentially entrain the flow based on the equations that we have. And then finally, the product water gets inserted back into the ocean, depending upon its density, wherever it's going to be neutral within the deep ocean. There are quite a few, and then the compensating flow, that this is the southward flow in general here, then the compensating barotropic flow occurs, again, by conservation of volume in the upper ocean, where we are not actually piping the stuff into the rock. And this parameterization reduced gravity formulations. We come up with the source waters based on the hydraulic theory. Entrainment is given by single point entrainment parameterization. Simply then the product water is the sum of the source and the entrainment. It's just conservation of volume. And then finally, tracer equations, temperature and salinity, again, they are essentially simply using temperature and salinity conservation based on the amount of available entrainment volume and the source and the product volumes. So end result is essentially quite impressive. This is showing the volume transport in comparison with some available observations. As I was indicating earlier, you need to validate your parameterization against available observations. And these are at different longitudes and different density classes. Without overflows, we get these transports. But with the overflows, you can see that the transports increase quite substantially, matching the observations quite nicely, except at 69 degrees west. We still have a problem there, but still we get higher flow rates. So we can't fix everything, but this parameterization fixes quite a few of the things. So as I said, one of the issues with the overflow parameterization was the shallow depth of the overturning circulation in the Atlantic Ocean. This is showing the AMOC, Atlantic Meridional Overturning Circulation. The top row is for ocean-only simulations. The bottom is from coupled simulations. And just for reference purposes, I drew a line here at 3,000 meter depth. You can see that without the overflows, we are too shallow. Observations are indicating that this should be actually down to like 4,000 or 4,500 meters, this zero contour. And with the overflow parameterization, you can see that we are accomplishing that in the force cases. And in the coupled simulation, that's also the case. So this is actually a success. However, even if we have the best overflow parameterization in the world, if the surface fluxes are garbage, then we are not going to actually form the source waters needed for the overflows. So in that case, we are at the mercy of the surface fluxes and atmospheric model. And finally, I just wanted to show you what we do for estuaries, and this is essentially related to our river runoff parameterization. So this is a schematic of sort of our model. On the left side, we see the land model, and there's the river transport model. It sort of accumulates what the runoff should be in certain places. And this is the pop grid on the right-hand side. So what we do is essentially, regularly, this is shown by a sprinkler here, we simply take this incoming runoff and spread it over, I don't know, over a 300-kilometer sort of wide region. And it is many, many grid boxes. So that's what we end up using traditionally. And this is not really a good way of doing it, but it's really practical and it's an easy thing to do. So in our section with university collaborators, they actually implemented a river runoff and estuary box model. So what this parameterization does is it actually accounts for mixing that happens in the estuaries. And the left side here is where the estuary is. And then the right side is showing the sort of vertical distribution of ocean grids next to the land boundary. So it accounts for it is essentially, I mean, it's the Qs or these arrows are showing simply volume conservation. And based on parameterizations that's happening inside here, exchanges, then it determines what the salinity content should be and how it should be distributed in the vertical. We have used this thing not for all of the runoffs, but we are using it, I think, for about 19 primary rivers, Amazon, Congo, and others. So this is clearly a more realistic representation of the river runoff and estuaries. So with that, I would like to sort of show this slide again. This is my last slide. As I was mentioning on Monday, there are machine learning efforts within LEAP, within M-squared lines, targeting some of the parameterizations that I talked about just now. And for example, the purple ones are actually targeted by M-squared lines. As I tried to highlight, they are actually using machine learning techniques to determine the shape function within the K-profile parameterization. There is ongoing work replacing GM parameterization with its machine learned sort of equivalent. And then I should have included one more thing here, which seems to be missing, is the horizontal viscosities are being also replaced by their machine learning equivalents. And so there is quite a bit of work going on. But as I said, I'm a little bit sort of cautiously optimistic, I guess. At most of these parameterizations are online, and they are actually costing at the moment more than the actual parameterization itself with mixed results. So I think maybe emulator approach might be better. Again, I mean, this is open field and much more work is needed to determine which path is going to be more beneficial in terms of reducing model biases as well as doing it in an economical way. So with that, I'll stop and take any questions that you may have, either for today or any other on Monday or Tuesday lectures as well. Thank you.
Thanks a lot, Gokhan. Thanks a lot for your very detailed explanations of the of these Earth system models, their inner workings, and so on, especially the ocean component. Based on your talk today as well as the last 2 days, like anyone, any questions from the audience? Floor is open.
Thank you, Gokhan. And this is Professor Goswami. First of all, I must thank you for the lovely 3 lectures. I think they have been very, very useful for the group of people here. And coming from someone who has been involved in this development of all these parameterizations and the processes of the ocean modeling, I think this has been extremely good. And I want to thank you for your time and
You're welcome.
So I have a general question. So I'm basically interested in I'm more of a climate air sea interaction person, though. So I am more interested in the biases of SST simulations, especially in the tropics. And you have shown in one of your first lecture that there are still in the Indian Ocean, for example, we have biases of the order of 1.5 degrees, positive bias, negative bias in one of the slides. So there are part of that is attributed to the vertical mixing parameterizations, I suppose, under different stratifications. My question is that I think that is very important for regions like Indian Ocean and the monsoon and all that, you know, sort of the variability. Simulation of the variability correctly and for seasonal prediction as well. So because here the interannual variations of this monthly mean or the seasonal mean SST is of the order of 0.5 degrees Celsius. Okay, but if your bias is like 1.5 degrees, and we have a big problem in making the seasonal prediction. Now, if that is associated, is largely probably is over mixing or under mixing due to the mixing parameterizations. And that is, so the KPP doesn't seem to work. So the question is, what is the future and what is the development in this? I have been sort of, I'm out of, sort of this development going on in this field. And what is your vision into sort of improving these biases in this?
Yeah, I mean, I guess they're called persistent biases for a reason. And some of the biases that you mentioned, in particular, I think this is the slide that you were mentioning. These are, in addition to the Western boundary biases here and the Gulf Stream biases, the tropical Pacific biases have been rather persistent. And I mean, major impact of these biases also, well, I should be careful what I'm saying here. There are also associated ENSO biases. So both in magnitude, in phasing, and teleconnection patterns. In fact, we are actually currently focusing on, we still have major biases in ENSO in CSM3 as we develop it with MOM6. We have tried quite a few approaches. And initially, you are absolutely correct that we thought that it was primarily associated with oceanic mixing, and we played with those. It doesn't seem to be impacting the results that much. We are actually looking at land biases, and especially over the maritime continent region. And So anyway, there are, I think these biases have been really there, and regardless of which parameterization we look at, they don't seem to be sort of impacting. I mean, there are impacts, but they are not solving the problem. Another problem is that with answer-related SST biases is that you need to really have long simulations to assess the ENSO and teleconnection patterns and how the mean state biases might be impacting it, because their statistical properties are not really stationary in time. So, so on that is that, and then there are other schemes, of course, as you mentioned, maybe for vertical mixing. So just recently, Belarge actually revised the KPP scheme, and he made it more energetically consistent. And as we speak, we are trying its impacts, whether it's going to impact or how it's going to impact these SST biases. So stay tuned for that. But I don't have I mean, I don't have a better answer than that, unfortunately.
Just a short follow-up. I understand that over the last few years in India, I think we have done some very high resolution observations in the Ocean Bay of Bengal, and under our monsoon mission project, and which I sort of initiated. But in that project, we have learned something interesting, that over in places like Bay of Bengal, where the stratification is very important, mixing is contributed not only by these small scale eddies, but also by inner cell oscillations and sub-mesoscale eddies.
Absolutely, yes, yeah.
They contribute a lot, but none of these parameterizations include these in a comprehensive way. So, what is the thought?
So we do use sub-mesoscale parameterization in our model. So we do use it, but I did not cover it here. But it itself has quite a few challenges as well. Right now, the parameterization that we have in the PUP model is the one that I incorporated quite a few years ago. And as you may know, there is an upscaling factor that needs to be included in the sub-mesoscale parameterization. And that upscaling factor is inversely proportional with a length scale. It's supposedly representing the frontal length scale of the sub-mesoscale eddies. And what you use for that particular length scale changes your results quite significantly. And it is still a tuning exercise. And more recently, Bodner et al. Actually developed a version of that parameterization, which essentially, in a sense, diagnostically, well, it uses time and spatially evolving values for that related coefficient. But we are finding that it actually impacts results quite significantly, particularly in the Labrador Sea. And when I said yesterday or the other day, talked about the Labrador Sea issues, we are finding that sub-mesoscale mixing actually can impact what's happening in the Labrador Sea. But then again, as you said, there are air-sea interactions. If we have air-sea fluxes incorrect, and that is going to create issues as well. And then, especially with the shortwave coming in, that's dependent on the clouds and all that stuff. So it's all of the above. And we don't have a magic bullet to address all of those. And then I know that the Chinese folks at OUC, I believe, developed another parameterization. So one more thing that I should mention is that Langmuir mixing, right, with the waves and all that stuff, we do use Langmuir mixing, but how it's incorporated in the model is sort of crude at this point, in my view. So Bill is actually modifying that aspect as well. And wave models by themselves tend to be really coarse. They are very expensive. They are in the spectral space. I don't know whether finer wave representation will help these things or not, but it's many processes coming together.
Okay, thank you.
I don't think that I answered your question fully, but that's sort of where the things are.
Yeah, this discussion, I didn't have this question, but this discussion has triggered one. So I work on atmospheric processes. I have a question about this local versus non-local mixing. This is a kind of quite generic question. Do we know what portion of fluxes are non-local in the ocean versus local? That means only the adjacent layer and K diffusion can represent, I mean, our hope is K diffusion can represent it, or the higher moment closures might able to represent them.
Yeah, I mean, I don't know what fraction is local and non-local. I mean, it is happening. It should happen in convective situations. So to the extent that we have unstable conditions, the non-local mixing should kick in. But yeah, I mean, I used to know that fraction probably when I actually looked into it more detail, but I can't remember. But my understand, if I recall correctly, I may be wrong. I think it's a rather small fraction non-local mixing.
Okay, yeah. Thank you. Thank you, Gokhan.
Anyone? Yes.
Hi, sir. This is Triparna from IIT Kharagpur. Sir, I had a small question regarding today's lecture. So you were saying about mixing across isopycnal surfaces, that is dipycnal surfaces, which is constant in the upper surface. So I was thinking, is it because of the sizes of eddies being trapped, like they are smaller, so horizontal mixing is getting dominant? Something.
Well, yeah, I mean, it is, I would phrase it in a different way. It is, so if you look at the interior of, so if you look at sort of the isopycnal, those gray lines that I showed in that schematic, because at the surface, those isopycnals, well, most isopycnals, if there's going to be water mass formation, they need to outcrop, meaning that they are going to be in the vertical direction at the surface. So when they're in the vertical direction, that means you are not going, any mixing that you have in the vertical is part of the vertical mixing, but then any the mixing that you have in the horizontal, other mixing, horizontal mixing that you are going to have is going to be across isopycnal. So in a sense, horizontal mixing becomes dipycnal mixing, vertical mixing near the surface becomes along isopycnal mixing. So near surface eddy flux parameterization is trying to account for that. The GM parameterization, isopycnal mixing parameterization, is only valid in adiabatic conditions. So that means it's in the ocean interior. And in the past, we simply essentially set the coefficient, the diffusivity coefficient, to 0 near the surface. That's how we essentially accounted for that process. But that's not the right thing either, because in the ocean, at the surface, everything should be occurring along the horizontal direction, true horizontal direction.
Thank you, sir. And one more question from yesterday's lecture about time discretization. So you were talking about leapfrog scheme, which is a midway between explicit implicit. So is it because you're solving the SGS scales using implicit for gaining unconditional stability, or you're trying to solve advection diffusion using the same time steppings with this?
Yeah, if I understand your question correctly, I mean, leapfrog is sort of, it's going back to in ocean modeling to late 80s or whatever actually late 60s, and it is a well, it's a 2 time level scheme. And compared to more complicated higher order schemes like Rangekara and others, it is a lot cheaper. And it has, except having a split mode that I tried to explain with, which can be eliminated either by Robert filter or time stepping, it is a rather simple time-stepping scheme with what I would consider relatively good stability properties that can be, and conservation properties easily implemented in long simulations. As long as you lag, well, I mean, you have to lag the diffusion term and advection term is from the current time step, then it is a rather stable scheme. So that's, I think, the reasoning back then was just simply it's a simple scheme, cheap, and second order.
Thank you, sir.
Today, though, I mean, people are not happy about the split mode. And of course, when you do the averaging and Robert filter, then you have to be careful with the conservation properties, almost contradicting what I just said earlier. Some models use just forward time stepping. And I think MOM uses, I can't remember what order it is, but Rangekara scheme. So there are actually more complicated schemes in use today, but they are more expensive. I can't hear you anymore if you are talking.
Am I audible, sir?
Yeah, I can hear it. I can hear you now.
So, in today's lecture, you showed that when the heavy bottom water sinks along the bottom topography, it goes in a fashion of advection, convection, then advection along the bottom topography. And then you said that this will induce entrainment at different vertical layers. And in the next slide, you showed that the water mass goes from the surface along the hypotenuse to some lower surface. So I did not understand, why do you need that transition?
So what I meant by the original schematic was that if you have a level coordinate, z coordinate system, then if you are forming dense water at near the surface in the upper ocean, the only way that can go down and in the horizontal direction further south is a series of horizontal advection, convection in the vertical, horizontal advection, convection. So that steppy topography it then creates a lot of artificial mixing simply because of advection, convection going on. In reality, in observations, such mixing really doesn't happen because the flow goes pretty much along isopycnal surfaces. In a z-coordinate system, you cannot do that. And when a flow goes along isopycnals, then it just, with little mixing, it goes all the way to the bottom, much deeper levels, and wherever then it gets inserted in observations, wherever it is neutrally buoyant. So if you I was talking about the vertical coordinate systems yesterday. If you actually have an isopycnal coordinate system, then you do not worry about that spurious mixing. So that kind of spurious mixing is associated with level coordinate models, which is used still in many ocean models today.
So this means that the second schematic that you showed is for the isopycnal vertical quadrant.
It is essentially the second schematic that I showed is trying to mimic what would happen in an isopycnal sense, in a sense, and we are just piping through the rock the flow essentially in that way.
Thank you, sir.
Yeah.
Good morning, sir. I have two questions. First is from today's class and another is from yesterday. So like when you discuss the major scale tracer parameterization and the horizontal viscosity parameterization, you end up with a chart. Like for this scenario, for example, CFL condition gives that A should be greater than millions, and for other scenarios, you get A should be like greater than something or less than something. So in that slide, I saw some incompatibility, like values are very, very differing. Some is million, then
Yes.
some is immediately it is thousand or below thousand, something like that. So while setting your simulation, how do you choose a particular value of the parameter A and how it affects the other scenarios?
Yeah, I mean, that's another good question. It is when we actually implemented those, we had to try quite a few different approaches and different values. So as I indicated, we try to use, so you can think of it this way. A momentum mixing can be considered also as being done by mesoscale. And from the tracers, we know that that should be order 1,000 or something like that for realistic simulations, and from the observational estimates. So if you think of it from that point of view, then you can argue that perhaps the momentum diffusion or viscosity should be of the order of 1,000 or something like that. So we are trying to keep the viscosities as low as possible so that we can essentially have realistic current patterns. As I said, equatorial undercurrent is one of them, or western boundary currents. If you just have too large of a viscosity, too far out from the western boundaries or eastern coast of the continents, then you get essentially the Gulf Stream is not narrow. It's just so sluggish and wide. We don't want that happen. So we tried. So then what we do, we set them to as small values as possible. We need to make sure that the CFL conditions are satisfied, and usually they are. And then we need to also check the instantaneous velocity fields in the model. We run it, we essentially get daily out or actually time step output, and you'll see immediately that if your viscosity is too low, you'll get two grid point noise, especially in vertical velocity field near the western boundaries of the oceans. Then you have to subjectively decide how much of that noise you want to live with. And in POP, in CSM2, and in CSM3, probably to some degree, we have some noise, and we decided to live with some amount of subjectively determined noise. So that is trial and error. And as I said, usually in the ocean modeling community, viscosity is used to control noise, not necessarily for, I mean, we try to inject some physics in it to get realistic undercurrents and boundary currents.
Okay, sir. And another question is from yesterday's class. So, like yesterday you introduced the model, mathematical model, then you discretized it. You uh, gave some space discretization method to calculate the fluxes, then the time discretization. But at the end, I was actually eager to look at how do you balance your computation load. So do you use domain decomposition method or some other method to distribute the computation load among the processors?
Yeah, we use in this case MPI essentially. We use domain decomposition, and I can't remember how many we split it into, but we try to essentially balance it. In an ocean-only model simulation, I mean, you can divide it as you like. It doesn't really matter because it's just one component, and it's just a matter of how long you want to wait for 1 year of simulation or whatever. But in a coupled system, then we actually do each individual model has its MPI decomposition. Then we need to determine how to essentially use a given set of processors. We do some of them in parallel. We do some of them concurrent on different processors. And we try to optimize the number of years per day, as well as the processor count and the cost per year. So if you want to get really fast solutions, then we try to get ordered 30 years per day, but then the cost is higher. But if we don't need to get a result relatively quickly or for some other sort of lower priority projects, we have configurations of the model that can run cheaper, but then the number of simulation years per day will be order 10 or 15 years. So it's just a compromise in that case.
Okay, thanks a lot, Gokhan. And so for the sake of time, we'll cut short this Q&A session, which has already been quite long, which is of course a great thing. But we would let us now. So if anyone has any further questions, please feel free to submit them using the Google form, which I had shared earlier, and I'll route them to Gokhan. But now let's thank Gokhan a lot, especially for taking his time for these 3 lectures at our hour. That is very that's understandably inconvenient for him. I guess it's 10:30 p.m. in his place now. So and he has done it for 3 successive days. So I like a particularly big round of applause for Gokhan.
Thanks a lot, Gokhan.
Thank you, Roxy. I enjoyed it a lot. Thank you. Too bad that I couldn't be there in person.
Yeah. We also feel so. Anyways, so thanks a lot.